Hello, I'm Ruby. In this video, we will explore what the atomic weight of an element is, or its relative atomic mass. To understand atomic weight, we must know two things. First, how to represent an atom with its atomic number and mass number. And second, what isotopes are. When we represent an atom, we use a chemical symbol, its atomic number, and its mass number. In this case, we represent a hydrogen-1 atom. This atom has 1 proton, 0 neutrons, and 1 electron. If we look up the element hydrogen in the periodic table, we can find various data. Among these data, we find its atomic number and its chemical symbol, but we do not find its mass number. However, we can find its atomic weight or relative atomic mass. But what is the difference? Let's look at the two definitions. The mass number is the number of protons plus the number of neutrons in an atom, while atomic weight is the percentage average of the relative atomic masses of its isotopes, using 1/12 of a carbon-12 atom as the unit. It seems difficult, but it's easy. Let's break it down. Before we continue, let's clarify that the term atomic weight is synonymous with the relative atomic mass of an element. Now, let's continue. Let's start with the end of the definition. This circle represents a carbon-12 atom. If we divide it into 12 parts and weigh one of those parts, we get the mass of 1 AMU. 1 AMU equals 1.66054 times 10 to the power of -24 grams and is used as the unit for atomic weights. AMU stands for atomic mass unit. This number is the same as the number we see on the screen. Multiplying by 10 to the power of -24 means we need to move the decimal point 24 places to the left. So, a carbon-12 atom has 12 atomic mass units. Therefore, the relative atomic mass of a carbon-12 atom is 12 AMU. Let's look at the relative atomic mass of other atoms to understand the second part of the definition. For example, for a carbon-13, it is 13.0034 AMU. For a hydrogen-1, it is 1.0078 AMU. And for oxygen-16, it is 15.9949 AMU. These are relative atomic masses of atoms. The value of the relative atomic masses of atoms is slightly different from their mass number and uses AMU as the unit. If we want to determine the atomic weight of the carbon element, we have to use the relative atomic masses of all carbon isotopes. As the definition states, let's look at the first part of the definition. If you haven't heard of percentage averages, you probably know what an arithmetic average is. When we take 3 exams, we add the grades and divide the result by the number of grades we received. This gives us the average grade. In a percentage average, instead of adding each grade, we use the percentage corresponding to each grade. 1/3 of the exams have a grade of 8. This is 33.33% of the total exams. And 2/3 of the exams have a grade of 7. This is 66.66% of the total exams. Doing the math gives us the same final result as before. We can see the calculation is much simpler with the divisions done. This is very useful if we have many grades to average. As long as the percentages are the same, the average grade will be the same. Now that we have seen each part of the definition separately, let's put it all together. When working with atoms, we handle millions of atoms at once due to their small size. To illustrate, we represent 1,000 randomly chosen carbon atoms. We see that some are red and others are blue. The red ones represent carbon-12 atoms, and the blue ones represent carbon-13 atoms. Due to their different abundance in nature, out of 1,000 carbon atoms, 11 are carbon-13 atoms, and the rest are carbon-12 atoms. The result of the percentage average, based on the mass and abundance of those atoms, is the atomic weight of carbon. Any sample of carbon we take, whether large or small, will maintain the same abundance percentages for carbon-12 and carbon-13. Therefore, the atomic weight remains constant, regardless of the number of carbon atoms we have. Let's look at another example. For the element chlorine, the abundance of chlorine-35 is 75.76%, and chlorine-37 is 24.24%. We also have the relative atomic masses of each chlorine isotope. If we calculate the percentage average of the relative masses of its isotopes according to their abundance, we get an atomic weight of 35.45 AMU, which is the value we find in the periodic table. Now, let's look at the element boron. The abundance of boron-11 and boron-10 atoms is 80.1% and 19.9%, respectively. Taking into account the relative masses of boron isotopes and their natural abundance, we get a boron atomic weight of 10.81. In the next video, we will see the Bohr atomic model. See you later. Goodbye.